Everything we've done so far has been review, but we need to get into some rotation. And basically, what we need to talk about is how we're going to sprinkle rotation into all of our units from this point forward, so that way you can see how rotational things relate to every subject matter that we study, whether it be momentum or kinematics or something of that nature. So this is a review, or I mean, this has been a review, and now we're going to look at rotation. And we've looked at the linear qualities of position, velocity, acceleration, and we're going to start looking at their equivalents in rotational form. And since this is new stuff, it's what makes APC a little bit harder, is that we have to sprinkle rotation into every single unit and understand everything linear and then rotationally, and so on and so forth. So let's take a look at this circle in the bottom right hand corner, and you can see I've highlighted a section of it, or drawn on a section of it. That section of it will be known as X. So that section we covered on the outside part of the circle is X. But if we were to think of it in terms of the circle, like that radius moving across that section of X, that displacement of X, we will have carved out a pi piece, and that pi piece has an angle. And that angle is theta. And you've learned in one of your previous math classes in the past that arc length was, I think, S equals R times the angle theta. Well, we're going to do the same thing, but we're going to talk about it in terms of where X is equal to R, our radius, times theta. And the great thing about this relationship is if we were to draw a smaller circle with a smaller radius, the X distance changes. I don't go as far on my little small red circle there as I do on the big red circle, and you see that black portion there that we've covered X there. I don't go as far in the small red circle, but I still cover the same angle. So we got a different radius, same angle, and then for us, we can use position as our angle. They're very similar to each other, and our angle is X over R, or X equals R theta. So R is the radius and X is the position. And it's easy to do this because the angle will be the same for either one of these circles we've drawn. They have a different radius. We can find the different displacement or the different linear distance or displacement X that we're going to use. So basically the position we cover on the outside of the circle is our arc length, and then we're going to sweep through an angle that we're going to call theta, and they have a relationship where theta equals X over R, or X equals R theta. Now we can talk about velocity, and when we talk about velocity, if you remember, we had velocity equals displacement over the change in time. And we have a relationship for X where we plug in the R theta for X, and it's still over the change in time. But we also know that theta over t is equal to omega, or angular speed. And so when we talk about these things, we're talking about rotational or angular, but this is angular speed or angular velocity. So we can replace the theta over t with an omega, which represents our angular velocity. And so now our omega, or angular velocity, equals v over r, or v equals r times omega. So the next one we're going to look at is acceleration, where acceleration is now alpha, which stands for angular acceleration. And angular acceleration is equal to regular acceleration, linear acceleration, divided by the radius, or acceleration equals r alpha. And we're going to be using these things. We're going to be using these things interchangeably, and we're going to look at when or how we use them. So let's go into our first example, where we're going to have a bicycle wheel with a radius of 0.5 meters, and the center of this bicycle wheel is traveling at a velocity of 10 meters per second. Now, as this bicycle rolls, we're going to assume that the bicycle is going to roll without friction, or without slipping, which means it's going to have friction. And as long as it has friction, all of our relationships are true. So our displacement, our velocity, and our acceleration are all in a relationship with our angular quantities. So displacement equals r theta, velocity equals r omega, and acceleration equals r alpha. So looking at it with our velocity of 10 meters per second, we'll just say our time is going to be 2 seconds. We can find a quick distance it's going to travel as 20 meters. But let's say I want to know how many turns it's going to make. So when trying to figure out how many turns it's going to go through, we have to look at the angle that it's going to sweep through there and how many times that angle is going to happen. 360 degrees how many times, or 2 pi how many times. And so that's why I underlined the theta there. And then the other thing we can look at is the relationship between the other quantities. So omega is theta, change in theta over change in t, and alpha is the change in omega over the change in t. Where basically those are the, just like velocity equals the change in displacement over time, now we're looking at the exact same thing in an angular quantity, where the angular velocity equals the angle that is going through over a certain amount of time, and the angular acceleration equals the angular change in angular velocity over a certain amount of time. And for those of you in BC calculus, it is the derivative of the angle over with respect to time, and the derivative of angular velocity with respect to time. So to start figuring out how many turns, we have to take what we're given linearly and what we calculated as our linear displacement and be able to turn it into rotational or angular quantities. And so at that point, we take our givens and recognize we can use angular velocity is equal to the linear velocity divided by the radius, and we take 10 meters per second divided by 0.5 meters, and we get 20 some distance over seconds. And the distance we use is going to be radians. We cover that much distance, or length really is probably the better term, length over seconds, and so we're going to use radians for that. Radian happens to be how we measure angle, and we should all be familiar with that from AP1, and 2 pi radians is equal to 360 degrees, so a full circle. The next thing we can do is reorganize the angular velocity equation to where it works for theta, and so theta will equal angular velocity times time, and we can take our angular velocity of 20 radians per second and multiply it by a time of 2 seconds, and we get the angle theta is covered 40 radians. Another way to do this is to take your delta x, your displacement, which is 20 meters, and use the equation where delta x equals r theta, where theta is 20 meters. I'm sorry, delta x is 20 meters, and theta equals delta x over r, and delta x over r, the displacement over r, is 20 divided by 0.5, which is 40 radians. The other thing that we need to notice here, first off, is we end up with no units. If you look at that equation, 20 meters over 0.5 meters, the meters cancel. And when you have no units, you just substitute radians in immediately, because that's what we're left with. And at that point, we can take our radians and then turn it into how many turns we're looking for. And one turn is 360 degrees, and 360 degrees is 2 pi radians. So we do 1 turn equals 2 pi radians, and the radians can cancel, and we're left with 40 times 1 divided by 2 pi, and we get 6.4 turns. Either way you do the equation, whether you solve it, with starting with the change in displacement is 20 meters and using displacement equals r theta, or turning it into angular quantities and getting 40 radians. You get 40 radians either way. We just have to, at that point, turn it into how many turns, how many rotations, how many revolutions, something of that nature, and it's related to 2 pi. All right, another thing we're going to look at the linear quantities on one side and the rotational quantities on another. So on the linear side we have x, and then we have velocity equals the change in x over the change in time, and we have acceleration equals the change in velocity over the change in time. So all things you learned in AP Physics 1. And then we have our kinematic equations where v equals v naught plus at, and v squared equals v naught squared plus 2a change in x, or displacement. And we have displacement, or change in x, equals v naught t plus 1/2 at squared. And then on the rotational side, we have their matching quantities or equations, where x is going to be equal to theta, or the angle in which we sweep through, and then angular velocity is equal to the change in theta over change in time, and then angular acceleration is equal to the change in omega over the change in time. And then we can supplement all of the quantities that we know for rotation, or angular quantities, into the kinematic equations. And so at that point, those three kinematic equations match up with our other kinematic equations for linear. And these are the things that we're going to use primarily for this part of the unit. It's not new equations, it's not new variables. You learn these things in AP Physics 1, but what we're going to do with them is going to be a little bit new to you in AP Physics C. So stay tuned. We have one more video that we've got to go through that shows you what we're doing that is new.